Saxon Advanced Mathematics, Lesson 12, Geometry. Pretty easy, pretty straightforward, a lot of review. It'll be fine. First, we're talking about angles and polygons. First, we want to talk about interior angles. That's what we usually talk about, the ones that are on the inside of the shapes. You've seen this idea expressed different ways. If we assign the interior angles of any shape of triangle, this one looks vaguely equilateral, but it doesn't have to be. Any triangle, if you add x plus y plus z, you will get 180 degrees. It's a lovely thing about it, right? This is very helpful to us when we're looking at larger polygons, quadrilaterals, pentagons, hexagons, etc., 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 right? What we can do is if we want to know how many degrees are in a shape, let's say a quadrilateral, what we do is we pick one corner and we draw a line to any other vertices that we can connect to. We've already gone from here to here. We've already gone from here to here. So we add a third line there. Now we have two triangles. We know that each of these is worth 180 degrees. So that tells us that the total number of degrees in a quadrilateral are 360. If we're doing a pentagon, 1, 2, 3, 4, 5. Same thing, we start here and we draw a line to every corner that doesn't already have a line connecting it. We've got one there, so we need to go here, and we need to go here, and then we've already got one to that corner. So there's 180 degrees there, 180 degrees there, and then 180 degrees down there. 3 times 180 is 540 degrees. See? So easy and so simple. Let's do one more. 6-sided object. And again, this isn't true just for perfectly drawn ones. I'm intentionally drawing mine a little wonky, just so you can see it doesn't matter if they're perfect or not. Okay, from here to here, we've already got a line. So I need to draw a line there, and I need to draw one there, and I need to draw one there, and then I've already got one there. Okay, so that's 1, 2, 3, 4 times 180, 720 degrees. And I'll just remind you, this is how I got that number, and this is 4 times 180. So there is a nifty little formula that we can use to find the number of diagonals where n equals the number of sides. Remember that in addition to meaning hashtag, that sign also means number. So if we want to know how many diagonals that we need to draw in, we count the number of sides. We multiply it by n minus 3 and divide it by 2. So in a 6-sided object, there are 6 sides. 6 times 6 minus 3 is 3. 6 times 3 is 18 divided by 2. There are 9 diagonals in all. Why would we need to use that number? I don't know. Let me get back to you on that. I think that's the total number of diagonals possible, but we're not trying to draw all the diagonals, are we? We're just picking one corner and we're drawing all the diagonals from that corner. Okay, this is what I really want you to take away from this. Don't think about that. I'm not sure what to say about that. I don't think I like that. But to find the interior angles in a shape that is bigger than a triangle, we take the shape and divide it into triangles by going to one corner and drawing out any extra lines we need to connect so that this dot connects to every other corner, right? And on the 2 dots on either side of our dot, we'll already have a line there, so we don't have to draw anything. But to all the other ones, we'll add those. And I did the same thing here. I picked this corner. You can start in any corner you want. Just work from one corner to all the other points. And then we did the same thing here. Okay, super nifty, useful tool. That's what I want to say about interior angles about polygons. Now let's talk for a minute about exterior angles. Here's a triangle. We know that the interior angles add up to 180, right? But what if, let's just extend each one of these lines. What if you wanted to measure these exterior angles, right? The rest of the triangle. How could you calculate what these angles total? We just want to talk about the total. Well, here's the best way to imagine it. Here's us. Here, we'll go together. I'll go with you. We're going to walk around this, and as we do, we're going to be adding up all of these exterior angles. When we get back to the beginning, we will have counted all the angles and we will added them together. They will always equal 360 degrees because we walk in a circle all the way around it, right? It's kind of it's so obvious it's hard kind of a thing, but it's not really hard. Exterior angles of a polygon always equal 360 degrees, always. There's only one caveat. Polygons that have caves in them. Okay, this is a polygon that has a cave in it, right? As we walk around it, we're not taking into account these weird little spaces, are we? There's one here. So this walk around the circle and get 360 only works for polygons that don't have caves in them. If we've got caves, then we're creating extra angles and that throws things off. So concave polygons don't get to be part of our club. All right, we're almost done. The next topic, which I'm going to touch on briefly, it's something called the chord tangent theorem. Now you remember we talked about how theorems are rules that can be proven. So when we hear that there's a theorem, we know, oh, there's probably a proof to go with this. John goes into quite a bit of detail in explaining this proof to you, but it's too advanced for where you're at right now in your proof education. I don't want to dump this on you. You're not ready for how detailed this gets. What this proof proves, I'm just going to introduce you to the idea of it without dragging you through all the details. You know how we talked about with an inscribed angle? Let me write it before I say it. There's always this relationship between the inscribed angle and what we call the intercepted arc. And we talked about it last time, and I'm going to say it again. The inscribed angle is equal to half of the intercepted arc. And then if we reverse it and we talk about the intercepted arc first, the intercepted arc equals half of the inscribed, or 2 times rather, 2 times the inscribed angle. okay? The words gets twisted around, but you can easily say this is the smaller one, that's the bigger one, so this is the one that's half and that's the one that's double, depending on which way you're looking at it, right? Now, how do we know that's true? Well, there's this thing called the chord tangent theorem that helps prove it to us, and I'm just going to introduce you to the idea. Like I said, here's the center of a circle, and here is a line that comes straight through it. It divides it in half. Here is a tangent, a line that connects only at one point, and it connects, and always, tangents always make a perpendicular with the line that the radius or diameter in this case. They always connect and make a 90-degree angle here, right? So I'm going to put some letters on this so we can talk about this. Okay, now I want you first to look at this angle that we've made here. Angle BAC equals 90 degrees. Would you agree? We know that because this forms a tangent that always creates a right angle. Tangents always create a right angle with the radius that they intersect with. And OA is the radius, BA is the diameter, all right? So this angle is a right angle. This, and it doesn't necessarily look like it, this whole line here is the intercepted arc of that angle. It looks a little weird, but it's true, right? If BAC were a mouth, this is what it would bite, right? So arc, well, not arch, arc BXA is the intercepted arc, right? I'm going to write intercepted there too. BXA, this arc, is equal to how much? Well, it's half the circle, right? Because this is the diameter and it cuts it in half. Pretend it's perfect. Mine's not perfect. That must be then 180 degrees. Because it's half of 360, right? 360 would be the whole thing. So we just proved that angle BAC equals 1/2 of the arc BXA. Oh, we proved it through this little, we talked through a proof of it. This isn't a formal proof, but you get the idea. And then we could say, conversely, if we wanted to, we could say the arc BXA equals twice the angle BAC, because BAC is 90 and the arc of BXA is 180. So this is the proof that proves the theorem. And that's how we know this about inscribed angles. Okay, this is a rule that we've accepted. This is the beginning of the proof of it. John goes ahead and refines this a little bit further, but if you can just understand this much of it, I'll be very happy. Okay, so this is the proof of the chord tangent theorem. What John goes ahead and does is, well, what if your angle is bigger than 90 degrees? And what if your angle is smaller than 90 degrees? He talks about those two situations. But if you can understand this, that makes me very happy. That's the proof. And I'm just double checking. I believe there are no problems that ask you to do this proof, right? This is just for your, it's just for your education. This is called case 1. And I think he does them with Roman numerals, yeah. So this is case 1 of the proof. This is where the diameter goes straight through. And like I said, he does another one where the angle's bigger than 90 degrees and another one where the angle's smaller than 90 degrees. And he proves that this will still be true even in those two cases. And that's all. There are questions about the interior angles that we talked about earlier, but there are no questions about this in the homework, as far as I can tell. If you find any, let me know. All right, guess what? That was a short lesson, wasn't it? We're done with lesson 12. Be sure to check in with me this week and let me know how you're doing. If you are a student who's found me on YouTube and is watching that way, welcome. Glad you're here. If you would ever like to ask me any questions or clarify anything, you can reach out to me through my email, which is on my About page in a couple different places. So feel free to find me there. Okay, that's all. Goodbye.